Big data is cursed. In particular, we're going to look at two curses, the curse of dimensionality in high dimensional spaces and the curse of computational complexity. So what we've seen so far is that big data is high volume, it's large, and high variety, lots of different data types, many interdependent processes. And that means that every big data problem is unique. There are no always do it this way methods in working with big data. So you might say, well, just avoid big data then. Just do better data collection, better sampling, so on and so forth. There's a huge upside to big data. High volume means lots of useful information, actionable information, and the results tend to be reproducible, reliable, and robust. High variety means there's no limit to what we can call data. Images, tweets, documents, video, automobiles, airplanes. And we have the ability to create, study, and analyze, learn representations of very complex structures and data. That is, we can do things in science, engineering, business, and so on and so forth, things that we've never been able to do before. But there's a downside. High velocity means large data can occur so quickly or require algorithms that run so slowly that the results are produced too slowly to be useful. So look at an example, the subset sum problem. Given a set S of positive and negative integers, find the largest subset whose sum is 0. So here's such a set of uh, integers. Notice that -1 and 1 adds up to 0. Is there a larger subset? In other words, higher cardinality, more elements? Well, it turns out there is. So -1 plus 4 is 3, plus -7 is -4, plus 19 is 15, minus 9 is 6, plus -6 is 0. But if I had a set of 250 integers, that would be 2 to the 250, which is 1.8 times 10 to the 75th subsets. This problem, which is 250 integers, would take more than 10 to the 51st years on Oak Ridge National Laboratory's Titan supercomputer. And big data is cursed. In high dimensional space, a nearest neighbor may be very far away and kind of isolated. The more space to search, the slower the algorithm. The farther apart, the less reliable the relationship. High dimensional here means that the data is sampled from a large number of independent variables or features. So for example, a 1000 by 1000 grayscale image has 1 million independent variables. Every pixel is a feature. This curse of high dimensionality can lead to both unreliable results and huge calculation times. For example, hypercubes. Here our variables are going to have only two possible values, true 1 or false 0. And an m-dimensional hypercube is the set of all points in Rm whose coordinates are either 1s or 0s. So you could have, say, a point of all zeros, you could have the point 1, the rest are zeros, and so on and so forth. So we say that observations are adjacent if they differ in only one feature or factor. So here's the hypercube in 2 dimensions. It's just the vertices of a square. The hypercube in 3 dimensions is the vertices of a cube. Now we can draw a line segment from all zeros to all ones, and this is what's known as the main diagonal of the hypercube. Well, how long is the main diagonal of the hypercube? Well, it's got a length of the square root of m, and m is very large. So even though the hypercube in any direction is always going from a minimum of 0 to a maximum of 1, the main diagonal is becoming arbitrarily large. Its length is going to infinity. What about the angle between the main diagonal and an axis? Well, for m equals 2, two-dimensional hypercube, such an angle is 45 degrees. And for the hypercube, the angle is 54.7 degrees. And as you let the m become arbitrarily large, notice that this angle approaches 90 degrees. So hypercubes are simpler than most big data, but they are high dimensional. And that means 2 points on an m-dimensional hypercube are as much as the square root of m apart. And m here can be very large. Remember, it corresponds to the number of samples, which may be trillions or even bigger. And so that means 2 points on an m-dimensional hypercube can be an incredibly far distance apart. Likewise, as the m becomes large, goes to infinity in some sense, theta sub m approaches 90 degrees. Likewise, big data can be spread across enormous distances in which any two observations are practically uncorrelated, i.e. at 90-degree angles. This is the curse of dimensionality. There's also the curse of phantom information. Big data often contains at least some random noise, so we're studying random variables. The randomness may or may not be important to the big data problem. You may also have random-like patterns, and they may be the answer you're looking for. Or they may be misleading, or they may simply be there. In fact, almost any pattern imaginable can be found in a sufficiently large and complex data set. So more rigorously, if y is a random variable, then Rf sub m of a pattern, that's the relative frequency of observing a pattern in m trials of y for some given pattern. Another way to think about it is if you have m trials and some pattern, then the relative frequency is the proportion or percentage of those trials where you see that pattern. The probability that y itself satisfies that pattern is the limit, as m goes to infinity, of the relative frequency of that pattern in m trials. A key concept, and what I really want you to get out of this, the probability is the limit. And the law of large numbers says if y has finite variance and expected value, then this limit exists that defines this probability. So big data fights the law and wins. Events with probability 0 can and do appear to occur in big data sets. For example, suppose we're recording heads and tails as we toss a coin, but that every now and then the coin lands balanced on its edge, standing straight up instead of heads or tails. In particular, let's suppose it happens no more than 1 time in 1,000 tosses, 2 times in 4,000, 3 times in 9,000, and in general, no more than m times in 1,000 m squared tosses. Well, the probability that the coin balances on edge is less or equal to limit as m goes to infinity m over 1,000 m squared, and that's 0. Now, what does this mean? This means that balance on edge occurring means heads or tails information is not available. So let's suppose we had some actual data, but every now and then we have NA, which means heads and tails information is not available. It's balanced on its edge. Now, even though the probability that we get an NA is 0, we still may see as many as 100 balances on edge outcomes in our data. So that may seem a little strange, but you have to remember that probability is a limit, and a probability of 0 is what happens in the limit. So we may get up to 10% of the observations where heads, tails outcome is not available, even though the probability of not available is 0. So how do we address these curses? Well, the following are going to be major themes for our entire class. We could map to a low dimensional space called an encoding and then map back to a high dimensional space. That's called a decoding. We might use relationships among some of the variables to restrict the model to a smaller region of feature space. That's called regularization. Regardless of dimension, if the data is linearly separable, then we can find a separating hyperplane. This is a very powerful way of dealing with these curses. And it's the one we're going to explore, although we'll look at the other two in detail later on in the course. If the data is linearly separable, then there is a separating hyperplane. For example, logistic regression. Suppose we have a binary labeled data set, features x1 to xn. So the grades data, for example, we want to obtain values for the parameters beta sub I, beta 0 up to beta sub n, such that beta sub I plus beta 0 x0 up to beta sub n xn is less than 0 for negatives, and that is greater than 0 for positives, or at least for some t in the real number line. For now, we're only going to consider the case t equals 0. This equation, beta sub I plus beta sub 1 x1 up to beta sub n xn, where the x's are variables and the betas are parameters, in other words, they have numerical values. This is an equation of an n-dimensional hyperplane, a separating hyperplane. But if this n is really large, it's going to be very difficult to imagine such a large dimensional setting with this hyperplane. So we're going to do a new approach. We're going to define a new variable z, which is beta sub I plus beta 1 x1 plus up to beta sub n xn. And notice now we want to find parameters such that z is less than 0 for negatives and z is greater than 0 for positives. So we're going to use the summation shorthand. Z is the summation over the beta sub kx. Now later we'll see that this z is an inner product of parameters and variables. But what we want to do next is define our response y to be a function of z. This means that we have a function of one variable. We can therefore make it a monotone increasing from 0 to 1, which is known as a sigmoidal function. So let y be sigma of z, where sigma of z is sigmoidal. In other words, looks something like that. Well, notice in this case, y is the probability of being in class 1. So it's a predictive model for a binary classifier. If this sum is less than 0, then that means z is less than 0, and it means that we're on the left-hand side, as you see here. If the sum of the base of k, x of k is greater than 0, the probability of being in class 1 is greater than 50%, we're over here on the right. And we can define y equals 1 over 1 plus e to the negative z, and this is a sigmoidal function which actually implements these ideas. It's known as the... So let's look at an example, our simulated grades. Can we predict if a student will pass or fail before they take the final exam? So this is a classification problem. We're using previous and the first 4 exams to predict passing. Can we predict y given x0, x1, x2, x3, x4? So we're going to have to use our problem-solving process. First task is always to explore the data, get up close and personal. So we want to understand the problem and devise a plan. We're going to be using pre-processing. So let's use our problem-solving process. We want to first explore the data. So here's some histograms for previous exam 1 and exam 2. We notice that most have not had calculus previously. The histograms show two very different but overlapping populations. Here's the rest of the exams, but we only want to predict pass from the first 4 exams, so we don't want to use exam 5, the final exam. How do we know if this data is linearly separable? Well, it probably isn't. We really do need to use more exploration. Now, a key concept here is we may have almost linearly separable binary data, and our algorithms may still be very accurate even if a few observations are in the margin. So notice that these observations are in the margin. The convex hulls now overlap. But if there's only a few samples within that overlap, then we got a good chance our algorithm will be a good one. So is grades data almost separable? Well, again, we have to do a lot more exploration. So scikit-learn has commands for estimating the parameters, the betas of the logistic model. So we import pandas and logistic regression, load our data. Our x's are previous in exam 1 to exam 4. So our y is just the pass column. We create a logistic regression object with no regularization, that's penalty equals none, fit to the x and y, and then score, and we get an accuracy of 94%. So for example, our first row, which is class 1, the probability that it's class 1 is practically 1. The second row is class 0. The probability that it's class 1 is very close to 0, so it's a good prediction that it's class 0. This is what the intercept looks like. This is the beta sub I, and these are the coefficients. Now, this means that beta hat sub I is negative 44.123. This hat means an estimated value for this parameter. And likewise, here's beta 0, beta 1, beta 2, beta 3, beta 4. The largest in this case is beta naught. Notice that our exams are on a 100-point scale, but previous is either 0 or 1. And that means that these parameter estimates seem to imply that whether or not they've had calculus previously is the most important factor. But that's misleading because all the exams are on a different scale than previous. So let's pre-process the data so that all the features are on the same scale. And we can just divide the exam scores by 100. And now everything is between 0 and 1. So we do this and it rescales our exam parameters. So beta sub I hasn't changed, but notice now the last exam, beta sub 4, seems to be the most significant, in other words, the largest parameter value. So when everything's on the same scale, exam 4 seems to be what's most important to predicting whether or not they pass the class. Now this penalty again is regularization. I could change it to L2, which limits the size of the sum of the squares of the parameters. But is logistic regression even the best approach for this problem? And is a simple rescaling the best pre-processing for this data? How cursed is this data? Well, we're only getting started. We are far from finished even with this simple example. So big data is cursed. The curse of dimensionality. High dimensional data is highly spread out, highly independent, little correlation when you're in very high dimensional settings. And not every pattern in big data is valid. This is the curse of phantom information. So we're going to have to use a problem-solving approach as we go forward. We're going to have to do exploration, pre-processing, representation, and only after that, choose an algorithm. And most importantly, we'll also need to do assessment, which we'll see later in the course.